SSD, solid state disk drive. SSD is popular, right? So the solid disk drive techniques used for your USB and SSD, SATA SSD drive, NVMe SSD for servers, and some more embedded flash memories. So solid disk drive is providing much faster access than hard disk, but these are interesting characteristics in the storage market. In network, the fast networking devices replace the old one. For example, 1G, 10G, 100G, 200G networks. The fast network device replace the old technique. But in storage, does SSD completely kill hard disk market? So no one can develop hard disk at all? No, right? These are reasons that we still SSD is invented more than 20 years, but we still have to run hard disk technique because hard disk takes its portion in the storage market. Well, how hard disk can survive even if there a fast competitor comes in? The reason is that cost per capacity. So hard disk is low, but per byte cost as hard disk is much cheaper than SSD. So if you can store some big old data which not frequently used, we call this kind of data is archival data. Hard disk is much better option than SSD. Okay, so data capacity is bigger and bigger to reduce the cost for this archival cold data. Hard disk takes its role for storing that kind of data. So storage market, in the storage market, there is some kind of good use case for hard disk. There's some good use case for SSD. Okay, so let's talk about SSD. So SSD has this logical view, which is array of NAND flash. Again, like hard disk, SSD is block type device. It's collection of blocks. And internally, each block has a number of pages. So pages are kind of, similar concept to sector in HDD. Okay, so these are basic unit for I/O, and which is like a sector in hard disk. The size of block or size of page depending on vendor. So Samsung, Micron, Hynix having a different block size, different page size. Today is getting larger. Okay, so these are blocks, and logically there is some kind of unit of I/O, which is pages, consist in several multiple pages consist in a block. So these pages are having a kind of flash cell. The flash cell is the minimal unit that store the information. There are several kind of flash cells: SLC, MLC, TLC. So SLC is the cell is used for 1 bit. So in SLC example, according to your SSD put the voltage, there are 2 distributions possible. Okay, so there's a reference point. Say, oh, this is 1, this is 0. Okay, so SLC has a single level. So one reference point to distinguish 0 or 1. Okay, MLC is multi-level cell is kind of a misleading name, but 2 bits cell. So there are multiple levels of distributions. So it is 2 bits for level. So 2 bits exist 3 reference points. So 2 to the 2, 4 bits. Actually, it can represent 4 bits for using this cell. What types of bits? Okay, And TLC having a 3-bit, so it can extend more bits. So what are consequences of this, increasing the bit per cell? So the same capacity, larger capacity, it guarantees much larger capacity. However, SSD, unlike hard disk, this distribution is not always beautiful like this one. Sometimes it's distorted, or some kind of reference pointer is hard to distinguish 0 and 1 when you are writing, when you put the voltage on the same cell. So there's a real reliability problem. That's kind of this wearing much more likely happen in TLC operation. So TLC is much less reliable. So there's some kind of bit error can likely to happen in the cell. Okay, so these are cons of TLC and multi-level cells. Okay, so these are kind of internal flash types, how the cells are stored information, and these are typical kind of applications using this flash, NAND flash. So flash drives, flash card, smartphones, eMMC, your MMC card, or UFS, universal flash storage card, popular SSD, SATA, NVMe SSD, and embedded devices using these NAND flash techniques. These are kind of anatomy of Samsung 850 EVO SATA SSDs. So if you can break down the SSD, there's some kind of actual flash cell. Okay, and I will talk about later. There's some kind of controller which performs important internal operation. We will soon talk about the role of SSD controller and DRAM. So this data comes to this DRAM and going to host. Okay, so similar to hard disk. So if you look at the SSD compared to hard disk in the I/O data path, it involves mechanical movement. However, all data movements from here to here is electronic. So hard disk SSD is much faster than hard disk. So these are popular modern Samsung SSD, and these are SATA SSDs. Capacity-wise, SSD is still today SSD providing good performance, good techniques to large capacity in put into the high density data cells to the limited form factor SSD, right? So this is because using the TLC is possible to up to this type of capacity. Most importantly, performance. In terms of performance, again, the enterprise SSD only has 112 megabyte per second, but SSD is sequential read-write performance is more than 5. Today, high-end SSD up to 300 megabyte per second for read performance. Sorry, read performance is 3 gigabyte per second. Write performance is like 700 megabyte per second. Some SSDs, popular SSDs. So in terms of performance, much faster. The biggest advantage of SSD is that the random. Hard disk randomly is terrible because of SIG. This SIG operation is not existing in the SSD. So comparing to SSD and hard disk, providing much better random write. This is I/O per second. So given the fixed amount of how many I/O operation happens per second, and SSD is kind of much faster in random operation. But cost, in terms of cost, SSD is around 5 times expensive than hard disk. Okay, these are basic comparisons, and but the SSD, which doesn't have any the mechanical part and the fast performance, but it has some well-known constraint. Most importantly, it does not support in-place update. This is because this is related to how SSDs internally store the bits using kind of insulator and the voltage. But let's not talk about kind of how SSD can insulate the voltages to represent bits. But well-known characteristic is this no in-place update. What does it mean? If you can having a sector lying on page 1, if you are trying to, let's say this is page 1, page number 1. So first write happen, you make the 1. But if you the second write to the same pages, you cannot modify one to the other one. Let's say this write is making writing data to 1. This write is data to 2. So first, when this cell is empty, you can make a data. You can make a data 1. But if you want to modify the same block to 2, it's impossible to. This operation is not possible. In place update is not possible. Okay, so because of that, SSD has some kind of more operation which is called remapping or address translation. Talk about later. So these are kind of most important internals, and the knowledge to understand SSD performance. So we will revisit this how SSD deal with this in place of this. This operation can happen in operating system, right? The storage device has to support some get around to support in place update. How to do that? And remapping. Okay. And then SSD sometimes having the errors. So depending on the SLC, MLC, and TLC, the error ratios are different. But some SSDs, when writing a data, the data cannot be correctly stored. Therefore, ECC, error correction code, is common in SSD implementation. Again, there are sometimes bad blocks happen. So these bad blocks, when you are writing some cells multiple times, then this cell lose a capability to store the data. So if one blocks contain multiple bad cells, then this goes to bad block. So flash internal hard disk of internal software has to hide this bad block using remapping. Okay, and again, unlike hard disk, the SSD has some kind of limited programming. I mean, writing data or erase. Erase operation is required for deleting data, and this number of cycles, the allowed operation is limited. So SLC is most reliable thing. So this 100K trial is possible, but more than that, the cell goes to bad. So can the bit error when you're writing your data. And MLC is much less, and TLC is also. TLC is much less than MLC, because there are multiple cells. Reliability, again, I say that using more bits, having a less reliability, which actually reflect the number of limited actual program and erase cycles. Okay. So this constraint has to be addressed. Mostly these in-place updates and hiding the bit blocks. So SSD having this new techniques. Before that, let's kind of zoom in SSD memory characteristics. Because SSD is not support in-place updates. To update operation has to perform in erase before write. So you can read it. Okay, so and you can write a program. So this cell bits 1 to 0. You may be confused and think about the writing looks like 0 to 1, but internally make this voltage distribution to 1 to 0 is much more reliable. So internally SSD, the data is written, the bit is written is indicate for 0. Okay, so then don't get confused. Erase make this bit 1. Okay, so here, the bit written here is, this is written and this is erased in the cell. Okay, so when you are writing this is kind of initially erased block. When you are writing these pages, these are the pages. When you're writing these pages, okay, and if you want to write again to this same block, no in-place update possible. So to support that, one way is erase entire block, okay, and write the block again. Okay, so if this block has to be used for writing of data, it erase first, and you can program it later. Okay, so the erase operation has to be bulk because of internal characteristics. Erase cannot happen in individual pages. So for programming, NOR Flash or NAND Flash basically page unit is basic unit for programming, writing of data, programming, aka writing. But erasing has to multiple. So multiple. It is we will this is say erase block, which contain multiple pages. The size of erase block is also depending on the vendor. Today, erase block is much larger, like 128 megabyte, or some vendors using the 1 gigabyte erase block in large capacity SSDs. So erase block is depending on the vendor, but much larger than pages. So these are characteristics. So I'm keep talking about how to handle these in-place updates and bad block using remapping. Recall that in hard disk we talk about LBA scheme, whether operating system looking at the entire storage space as LBA. Okay, so OS can see SSD as LBA space. And this LBA location is translated to actual physical location, physical address, aka page number. Okay, so this mapping require for LBA to physical. So mapping translation happens. So who performed this mapping? Called the Flash translation layer. So in Flash, there's SSD controller, which is kind of 1 gigahertz ARM CPU, for example, which performs lots of computation operation. So most important functionality of SSD controller is FTL. FTL is Flash translation layer. Okay, so again, internally, SSD having a level of indirection, which translates LBA to physical disk space. That's the first one. And second one is that this file system in POSIX API is reading, writing sector, but internally to support update operation, SSD supports read and write operation and also erase operation. Okay, so this interface of file system and this interface of file system is mismatched. One way is that this interface is exposed to file system, and file system performs erase operation, which is kind of hassle. So better ways than in SSD, there are FTL, which takes kind of file system interface, read and write, and internally translate this command into read and write erase operation. Okay, this is FTL. Device driver putting here is confusing, but let's not talk about it. Device driver is existing host system. So Flash FTL originally placed in the host system, operating system. Now FTL is completely implemented hardware. The better way is they are putting the FTL into SSD. But earlier type of SSD, FTL was exposed to host, so operating system implementing FTL layer in software, but hardware implementation is what's common today. Okay, so this is hardware implementation. Right. So these are logical diagram of SSD internal. So this host interface controller sending data. So using kind of DMA operation and port map IO operation, interrupt, all this interface functionalities implemented in the host interface controller. And there's embedded CPU, as I said, and the small SRAM, which performs this translation operation. And there's DRAM controller, which connected to DRAM for DMA. Okay, and flash controller, which performs FTL, flash translation layer, and put several flash memory buses in parallel. And here blocks and pages are located in different channels. There's a SSD internals. The core of FTL operation, again, saying that the LBA address space are located into then the flash pages. So here's the example. Let's say you want to write a data. So operating system issuing the command in terms of number of LBA address space, LBA block number, and FTL has internal mapping table, okay, which performing the data. Okay, and if mapping table in place update, because SSD does not support in place update, all the data cannot be changed. Instead, this new write are all located in new location. So, for example, this is page 1. So this is page 10. So internal FTL allocate assign new pages for storing new data and change mapping, and then make old data invalidate, so that this write operation goes to these new pages. Okay, so these are ways that how SSD handle this in place update operation using this mapping table in FTL. So here are some series of examples of page mapping. So flash, let's say this in the example, the page size is 4 kilobyte. Today, the page size is bigger. 4 kilobyte is kind of basic. So I give you an example of 4 kilobyte page size, and each blocks contain 4 pages. So each blocks contain 4 pages. Okay, so let's say this is current state. This write page to this state, and then let's say trying to reading page 5. So host want to reading the page number 5, then it first goes to mapping table. So these are LBA. These are actual kind of physical page location, PPN. Okay, physical page location. So this 5 is LBA location. So looking at this sequential table and located this 5 and identify that this page table says physical page number 5 having this logical page 5, so goes to this block and read it. Okay, and then now this 3 request comes. First, I want to write some data to page 9. So page 9. So this logical page is empty. So allocate new block. So typically sequentially allocate. So depending on the allocation policies, it may change this, but for simplicity, let's FTL kind of sequentially allocate empty physical blocks. So here these pages are allocated for this data, write operation. So 6. So logical page 9 number 9 and allocate physical block is 6. For this 9 is required for recording. This is kind of reverse mapping. So when you are looking at this physical page number, I want to update page table. So instead of searching that, by looking at this information, oh, these entries are related to my data. So this is reverse mapping information. Reverse mapping information is required for update operation. We talk about later. And then the next is writing data to logical page 3, then logical page 3. Oh, sorry, 3. So 3, allocate new block 7. 7 and mark this allocate physical block 7 and mark this physical block 7 is used by logical block 3. And then next operation is 5. But 5, there already exists data. So SSD does not allow in-place update. So 5, physical block 5, this data has to be, placed different location. So SSD first invalidate this block. So this is invalidation operation. Then allocate new block for this write, which is physical block 8, and then update mapping to 8. So when you're updating this operation, it's first looking at the physical frame 5, and then see, oh, this 5 location is here. So to see that, to see PPN and to locate the local page number, it refers this reverse mapping and invalidate it and allocate new block. Okay, so that is used for invalidation, and these are kind of internally what happens for SSD in case of in place update. Okay, again, in operating systems perspective, these are done in hardware, so OS file system never care about this internal remapping operation. So SSD FTL engineers providing good FTL algorithms to allocate and internally invalidate operation in hardware. So OS designers are free from these details. Okay, so to support SSD, there are some many many things you have to consider. So in defragmentation, for example, you can moving around disk location to physically contiguously allocate blocks. So in an SSD, defragment operation is important because data is placed sequentially. So many IOs performed in sequential. But in SSD, the physical block is kind of located in internal hardware, and operating system does not know internal layout of the SSD. So defragmentation usually hard disk are not applied to SSD. So turn off that. And there is some kind of new command of trim. So okay, so trim command is kind of delete operation, but let's not talk about trim command for SSD. An SSD having much simple IO schedule. Why? An SSD in hard disk, it has some sophisticated disk scheduling algorithm required to reduce seek time, but SSD doesn't have notion like seek time. So IO schedule itself is much simpler. Okay. So and align the file system partition is the SSD layout. So file system can use the SSD's layout, and logical file system access is in the logical block number. There are some special file system called FTFS These are not this only kind of tailored toward for better using the SSD. So you are using the Android by default using this F2FS file system for your flash device. And block size is large, 4 kilobyte, and then in a hard disk, sector size was 512 byte, but now it's increased to 4 kilobyte. In SSD, the page size was 4 kilobyte, now it's increasing to 16 kilobyte. So much block size large. Usually the block size is larger in SSD. Then there's a multi-stream interface which can parallelize SSD operation. But this file system can leverage this multi-stream interface to improving the bandwidth of SSD, but it's not focused on this course right now. All right, so here are summary. So SSD has clear pros and cons. The SSD is small, much lightweight, robust, and low cost, and takes low power, right? This is electronics. But hard disk using a lot of arms, mechanical movement, consume more power. It's good devices. However, to use SSD properly, there is some kind of extra effort to support this in-place updates using FTL. FTL support this in-place updates using this design concept of level of interaction. And sometimes erase operation happens, it takes a lot of time. So when SSD, when you're writing a data, if erase operation happens in the middle of your write operation, then your write operation is very slow. So that causes some requests takes much longer time than the other average write operation, which cause kind of unknown delay, because operating system's perspective, whether erase operation happens or not is not known to operating system. And erase unit is much bigger than read-write unit, so bulk erase happens and operating system, and then SSD, sometimes bit error, and there's limited lifetime. Okay, so this efficient hard software support is essential for performance and reliability. So good aspect of SSD is good performance, but to leverage these good benefits, good software support, file system support is essential. Okay, so that is all about I/O storage lecture.